Okay, in our last section, we introduced, well, we more than introduced the idea of the reaction quotient, but we mathematically introduced that last time. And we're going to use that again in this section to further explain Le Chatelier's principle. So again, we have some ideas about what reaction quotient is, and we've actually already talked about Q greater than K, Q less than K. We're not going to really get many opportunities to have Q equaling K, but if Q and K are the same, there's no net movement to the system. It's not going to go from reactant to product or product back to reactant. So we'll jump in here and we'll talk about how we're going to be using this K and Q. Okay, so predict the direction of the net change. So if we looked at a ICE table, and it says we have 1 molar concentrations of everything. And it says that at equilibrium, you're going to have 2.36 and 0.32 and 0.32. I think it becomes obvious which way this reaction has to shift. So you start off with 1 HI, you'd have to add HI. You would have to subtract on the product side. So we don't actually have to do much in the way of mathematics to figure out how this reaction is going to change. But let's do a little bit more than that. Let's practice how we're going to use these Q's and K's. So Q, the reaction quotient, uses initial concentrations. So we have 1 molar of the H2, 1 molar of the I2 divided by 1 molar of the HI, but remember that is a coefficient of 2. That's not going to make any difference for this one. So Q equals 1 in this case. K would be, again, everything but using equilibriums this time. So 0.32, 0.32 on the bottom, 2.36 squared, and that's going to give you a small K. We don't really need the answer, but I had previously done the math on that. So in this case, Q is greater than K. What does that mean? The reaction has to shift this way, and we've already shown those shifts with those signs. So we didn't really need to do the Q versus K to know that, but we did it anyhow. Okay, so we have another equilibrium reaction. We have a equilibrium constant of 115. We have 3 moles and a 1.5 liter. That's going to give us 3 divided by 1.5 is going to give you 2 molar of everything. So we could compare a Q with the K of 115. So Q would be HF as a initial molarity of 2 molar, coefficient of 2. And then we have 2 molars of the other 2 items. So I think that's going to be, they're not all going to be Q equals 1, but so far that's been the case. So this time Q is much smaller than K, so to reach equilibrium it's going to have to shift from left to right. So that is more of our traditional looking ICE tables, where you have the change being negatives on the reactant side and positives on the product side. So 2 minus x is 2 minus x. 2 minus x is 2 minus x. 2, remember it's 2 here, it wasn't 0 like we've maybe had with some other ones in the past. The change is not going to be x, it's going to be 2x because of coefficient of 2. So 2 plus 2x. And then we can solve for x just like we've been doing before. Equilibrium expression has a constant of 115 in this question. Up top was 2 plus 2x squared. On the bottom is 2 minus x, but that's times a 2 minus x, so I'm just going to go 2 minus x squared. So we take the square root of everything. Square root of 115 equals 2 plus 2x divided by 2 minus x. Rearrange this to solve for x and you get 1.53 molar. So is that our answer? No, it's for H2 and F2, you're going to have to do 2 minus 1.53, which is going to be 0.47 molar. And then for the HF concentration, you're going to have to do 2 plus 2x, and I think that's going to come out to be 5.06 molar. Okay. Remember that if you have a large K, these changes, these x's, or in this case 2x, are going to be significant. Does 2 minus 0.47, wait a minute, sorry, 1.53. 2 minus 1.53, that's a significant change. So large K's are going to give you very significant changes. Okay. We have the synthesis of ammonia. Which of the following diagrams corresponds to the reaction at equilibrium? So the K is shown to us as being greater than 1. Greater than 1 means that there's lots of reactant to product, not much in the way of product back to reactant. So if you have a K of greater than 1, you should have lots of product. So we should be finding one of these vessels that has lots of ammonia. And the only one that has lots of ammonia is this one. So I would say we would like C for that one. For the mixtures that are not at equilibrium, will a net reaction move in the forward or reverse directions to reach equilibrium? It's tough to I guess we're taking a snapshot of this, so I think these are mostly reactants, so this is going to have to move in the product towards the product, and same with this one here. Okay. Next question. So we have the reaction. Let's move that up just a little bit. Okay, so here's our reaction, and there is a equilibrium expression that goes with that. And we've had these kind of questions before. Here is our ICE table. We had 0.5 moles in a 1 liter container, so that's 0.5 molar. And we didn't have any of that chemical. So again, we've done this almost exact same type of question a number of times now. By the way, 54.3 means that these changes are going to be significant from the 0.5 initial molarity. So 54.3 equals 2x squared, and then on the bottom 0.5 minus x squared, because it's 0.5 minus x times 0.5 minus x. So take the square root, solve for x. I'm not going to continue to show that. It's the same mathematics over and over again that we've had now. And I did a little bit of rounding, but that's pretty close to the answer there, 0.393. Does that have a significant effect on 0.5? It does. So the concentrations at equilibrium for those two are 0.5 minus 0.393. So let's write that down here. And then for the HI, it's 2 times 0.393. Okay, so we've done that kind of question a number of times. But I think this next one's going to be, by the way, I thought we should do one of these for class. You will not get one of these on the AP test, this next question we're going to do, and you won't get it on my test. And if you start going down this route, something has gone a little bit awry. So we'll kind of get you up to speed with that kind of question here, and we'll tell you why it won't be on the test. But I think it will become evident why it's not going to be on the test. So with the same reaction, we have the H2. Move that up a little bit. I'm going to need all the room I can get for this one. H2 plus I2 making 2HI. Initial change equilibrium, but this time we have much different numbers. So I don't really have a lot of room right there, so I think I'm just going to use these arrows. Okay, we still have the minus x's. We still have the plus 2x. But now it's going to be, for the H2 equilibrium, it's going to be 0.00623 minus x. Okay. And then so forth for the other two. We'll have to use those numbers given to us. So equilibrium expression, 54.3, same equilibrium constant we had before. So I'm going to go look at the products, and the products are 0.0224 plus 2x, and the coefficient, power of 2. On the bottom, we have had, with each of these questions we've done so far, those equilibrium amounts have been identical. Well, they're not identical for this one. That's going to be problematic. So we have 0.00623 minus x, and we have 0.00414, minus x. So we've been able to take the square root of everything and then be able to solve for x, but you may notice that this is quadratic. So let me, I don't know if you guys would be doing this by hand or not, but back in my day we had to do this by hand. So foil the top, foil the bottom, rearrange everything so you're solving for, well, putting it into the quadratic formula so you're actually solving for 0. And to make things go just a little bit faster, I am going to, I've already done the foil on a piece of paper. Again, you might have had this in your graphing calculator, the quadratic setup. But I got that now. So again, I foiled the top, foiled the bottom, rearranged everything so I have the x squared together, the x together, numeric together. And then just to refresh your memory, again, most of you have a formula in your an app in your graphing calculator for the quadratic, but there's quadratic, and plug everything in. And I don't know if you remember, I don't know when you guys did quadratics, but you were always getting two answers. And sometimes the one answer is absolute gibberish. Sometimes it's not as gibberish. We have to kind of figure out which one is impossible. So one of these numbers, we would not be able to subtract it from 0.00623. It's too big. And that's the one that is too large, meaning that it's impossible. So therefore, that's got to be our X answer. So if I go, and I'm putting arrows in here because I just don't have enough room here to do all this work here. And we'd have to put it in for that value too. Okay, so you could do the rest, but the second question here says, why is this problem much harder to solve? I think it just became evident why it's much harder to solve. It's the quadratic. If you start going into the quadratic on any question for the test or for the AP exam, you've missed some sort of mathematical cue to somehow get you away from the quadratic. So with most of the questions we've been doing up to this point, we've been taking the square root of everything, and therefore we didn't need to use the quadratic. So again, there will not be any quadratic questions on the test or on the AP exam. The only place you'll see one is, I think there's also one in your homework that goes with this section. I don't think I have a lot of room here, but did I give myself, yeah, I did give myself enough room here. So determine the direction of the change in this reaction. That is going to be a Q versus K, so we'll have to solve for Q. Is the net reaction change in the reaction going to be very large or very small? Let's move that up a little. This one here, 1.6 times 10 to the fifth is a very small K value. So we can already answer this question. It's going to be a very small change. Will the initial molarity of NaCl change significantly? Well, we just said no. We'll explain it as we look at an ICE table. And then we'll solve for equilibrium concentrations. And then we'll try to figure out if we were correct or not. This is going to end up being a very typical styled question. I'm going to have to get my initial amounts here. So the NaCl, 1 mole in a 2-liter container, meaning we have 0.5 molarity of it. Whoops. Okay, so that'll give us a starting point there. So ICE table, I said we had 0.5 molar. We didn't have any products. It's gotta be, whoops. It's gotta be that way. You can't subtract from 0. So you didn't have to even do a Q versus K. If there's only reactants possible in initial, it's got to go to the right. Let's finish our IC table. I keep writing next there, but I want 2x. Why? Because there's a 2 in the coefficient. 0 plus 2x is 2x. 0 plus x is x. Now, we're going to modify some things here. Because that k is so small, that means that this 2 times x is a very small number. 0.5 minus something very small is likely to be approximately 0.5. Now you're probably asking yourself, wait a minute, how can Mr. McNally just make that assumption? I'm not, well, one, I've done a lot more of these questions than you have, but also I'm not going to buy into that assumption until we're done, and I'm going to double check and see if that worked. Okay? So 0 plus something very small is still going to be something very small. It won't be 0, so we're going to leave the 2x and the x in there. So our k expression, 1.6 times 10 to the negative fifth, equals 2x squared, because you have to take the coefficient and make a power of, and then x over here. And on the bottom, we think it's approximately 0.5. So we got the 0.5 times 1.6 times 10, to the negative fifth, equals 4x cubed. Okay. X equals, I did some rounding here. So does 0.013 impact 0.5? It's not much of an impact. I mean, does it impact? It does, very, very, very slightly. But let's go back and let's take a look at where we're able to make this assumption. So let's do our equilibrium expression. 2 times 0.013 squared. Whoops, the whole thing is squared. .013, and then on the bottom, 0.5. And when you do that math, there will be a little bit of a rounding change, but you get virtually the same k as the 1.6 times 10 to the negative fifth. So we can make that change. Both in the AP and in our textbooks, and pretty much this is universal with all the textbooks, they will allow you to make that assumption if the assumption was less than 5% off of that initial amount. And this is a way, because you're not going to be able to do the quadratic quickly enough to be able to get us through the questions we need to get through. So that will be something that we're going to make that assumption many times. And the clue is that you often will be able to make that assumption if the k is very small. And 10 to the negative fifth is a small k value. Okay, what we got here? I think this might be our last question. No, we got 2 questions, but yeah, like always, we got the answer already. More ammonia is added. So we've had this reaction a number of times here. That's not balanced. It doesn't really matter if this is balanced to answer this particular question, but now it's balanced. You add more of the ammonia. So here is where you're adding ammonia. If you add ammonia, what will happen? Well, your Q is going to increase because the NH3, the ammonia concentration or partial pressure, is going to be on the top of the fraction for our Q expression. So if Q gets bigger, reaction shifts to the left. So you would end up using up some of your ammonia and then making some H2 and making some N2. Okay, and those are not drawn to scale by any means there. So the only one that works out to that is D. Last question. Again, we always have the answers for these multiple choices. K is greater than 1. I don't know if we're going to need that or not. We have a 1 liter container. We have a 1.5 moles, we have a 1 moles, and we have a 2.5 moles. So those moles are going to be molarities because it's in a 1 liter container. And those are initial. So you can do a Q versus K. I haven't even gotten to the rest of the question other than I saw all these deal with Q versus K. And the K was given, so that means we must have to solve for Q. So those volumes and molarities, volumes and moles will give you molarity, and for the PCl5 it's 2.5. None of these have coefficients other than 1, so we're not going to have to worry about that. And then we have the 1.5 and the 1. Okay, so I don't know, you don't really need to do the actual math of that, but 2.5 divided by 1.5 is not going to get you something greater than 6.5. So Q is less than K. That means that it shifts to the right. So that still doesn't help us out entirely because it talks about the total pressure. Well, what do we got here? We have 2 gases, 2 moles of gas going to 1 mole of gas. So if it's proceeding from 2 gases to 1 gas, it's going to go down in pressure. So decrease or decrease. Well, why is it C instead of D? Because K is greater than Q or Q is less than K, whichever way you want to look at it. I think that might be it. It is. So remember that for homework, you might have to do a quadratic question, but you will not be doing quadratic for any test questions or any AP test in May question.